So, welcome everyone. My name's Tim. I'm one of the members of the Bishop Fox Red team and one of the developers working on Sliver, a C2 framework that was originally written by Joe DeMessi and Ronan Carvela to Bishop Fox employees, or should I say former for Joe. Anyway, today we're going to talk about encoders and different ways that data is masked in Sliver traffic. We're also going to look into how to extend it a bit, write some custom versions to try and modify traffic so that you can have your own version of an encoder. So we'll start with the basics first and talk about some of the default options that are available. I'll go ahead and generate an implant so we can quickly demo that. I'll just have it call over localhost. In my case, I'm on a macOS laptop, so it'll be using Darwin, and I'll just skip some of the obfuscation and add some debugging output. So if we go ahead and hit enter, it'll quickly generate an implant, which I'll just run in a separate screen. Oops. Oh. Okay. Just 1 second. We're running into a small bug here. All right. Well, while I look at that, let's talk about some of the source code. So when I generated my implant earlier, what happened in the background was the Sliver server copied over the implant code in a folder under Sliver. So if I go into my home directory and I check out Sliver, I'll have a folder called Slivers, right? And then since I created one for Darwin AMD64, if you look in there, we're going to see the particular implant that we just generated. So if we go take a look at that, we're going to eventually land in the source code of our implant. The reason it does this is when you hit generate, the backend server is going to embed a series of values into that implant. For example, cryptographic keys used for the communication, and then also some specific IDs used to uniquely identify the different types of encoders that are used during communication. So I'm quickly going to open up the S code so we can take a look at that and see what that looks like. So let's quickly open up the implant that we were taking a look at here. All right. So, like I mentioned, if you take a look at implant.go, for example, you're going to see different cryptographic keys that are used to encrypt communications between implants or between the implants and the server. In this case, we're interested in the encoders and specifically in encoders.go. If you take a look here, you're going to see a series of values hard-coded. Each of them are used to uniquely identify the type of encoder that is being used for the current message that is being sent back and forth. And that way the server and the implant both know which encoder and decoder to use during communications. And that way they can properly obfuscate and deobfuscate when sending messages back and forth. So I'll quickly set up our implant and we should be good to get started. Just quickly restart our server here. All right. Here we go. So If we take a look at Wireshark to see what that looks like, we should see a series of HTTP messages going back and forth. Right now, we don't have any commands running, so all you're going to have is empty responses with no content. If I go ahead and use a command, for example, pwd, and we take a look at Wireshark, we should see, so first off, a GET request followed by a POST request. If we take a look at the details of those by following the HTTP stream, you'll notice there's a parameter here with a number. This is used to identify the exact encoder that was used. And then here you have the actual encoded data. So if we take that number, we can quickly find which encoder was used. I'll just use Python to quickly walk through this. We remove any letters from that and then just do a modulus with this hard-coded value. If you take a look at the implant source code, it's right here, 65537. So if we do that modulus, we end up with this number, 60,459. Looking at the source code, this is the identifier for the gzip encoder ID. So the message right after that was encoded using this particular encoder, right? And Sliver will kind of randomly shuffle between all available encoders to avoid having repetition as much as possible and to try to obfuscate some of what it's doing. So if we take a look at the post request right after it, which is here, follow that stream, it should be, yeah, this is using a word dictionary based encoder where basically it'll capitalize different words, and it's based on the size of the word. It'll use that to hide a byte in the communication. But again, if we grab the unique identifier here, switch back to Python, remove any letter from there and do the same modulus, we'll end up with the unique identifier of that particular encoder. So if I look at the source code of the implant here, quickly double check this. Oh yeah, there we go. So if I look at the source code here, this time it used the English encoder ID. A different way to try that out would be just using curl with the Sliver server to try and retrieve the same output, which can be handy if you're testing out encoders. So let's go ahead and just do this. I'll kill our implant for now, and I'll run a pwd command. So what is basically happening right now is the server is waiting for our implant to call back and request any commands that are currently being run. So if I go to my shell here, I can type a curl command for localhost. Here I'm listening on port 80. I'll specify the encoder we want to use. For example, let's do PNG. So paste that in here. I need to change the curl user agent because that one is blocked by default. And then finally, we need to specify the session cookie of our currently running Sliver implant. So if we take a quick look at Wireshark, you'll notice here there is a cookie called language. This is just randomly generated. What you really need is the same name that was used previously and the ID that you're seeing here. So I'll just add that to our curl request. Make this a bit more verbose, and let's just output to a file. So looking at the response here, we got an HTTP 200 OK and the content type image PNG. If I go ahead and open the file I wrote this curl request to, you'll notice this is a valid PNG file. And same thing, if we take a look in Wireshark, we should be seeing the same traffic type here. So just a, yeah, here we go. Curl request was a PNG and the identifier to specify to the server that we're expecting the data in that particular format. And so by default, this is the way that Sliver would work if you don't specify any type of custom implant, custom encoder. If we talk about custom encoders, the way that is set up is using Wasm. So essentially, you can write some code using any Wasm compatible programming language, compile it to Wasm, and then load that in Sliver. So that is what we're going to walk through in a couple minutes. I'll just quickly jumping back to quickly jumping back to the source code. One thing to keep in mind with each of these encoders is they all use the same encoder interface. We essentially expect them to have an encode and a decode function that takes a byte array and returns a byte array. So if you look at any of these in the source code, for example, the base64 one, it has these two functions that are used as the to send data back and forth between the module and the encoder code. And so when we talk about using custom Wasm encoders, it's the exact same thing. We'll want your code to have both a decode and an encode export available that expects the same data types, so that we can send that code from the Sliver implant to your decoder and then back from your encoder to the Sliver implant. So if you take a look at the code on the repository, you should find, I believe there's one by default. There should be a hex Wasm encoder. I'll just quickly open up the source code on my end. So if I go here, cool. Yeah. So in server assets and then traffic encoders, if you look under there, you should find a folder called hex, and it has a small example of a Wasm-based encoder using Rust. The reason why we've used Rust in this one is, I'll get into that in a little bit, but it's essentially something to do with performance. But the main takeaway you should have here is we have these two functions, encode and decode, that each take and return a byte array, and that are exported and available through a Wasm interface here. So let's switch back to our Sliver server shell. If you look at the generate command, it actually has a subcommand called traffic encoders. If you hit generate traffic encoders, it'll show you any custom traffic encoders that have been loaded into the server. So I'll quickly show you what that looks like. Essentially, you hit generate traffic encoders, and then there's an add subcommand, and then you need to give it the path to the Wasm file that you've previously generated here. So if we go to server assets, should be here, yeah, hex.wasm. If I hit enter now, it'll load that custom encoder in the server and make it available for any implant that we generate after that. The first thing it'll do when loaded is run a quick check to make sure that all the data that is encoded is properly decoded. So it'll generate a bunch of random buffers containing random data, encoded, decoded, and make sure both of them match up. And then it'll also do a quick performance run to make sure, to give you an idea basically of how your encoder performs when working with different data sets, whether it's downloading a small file, or whether it's just running commands back and forth. The reason for that being that you're going to be a bit constrained with the type of encoder you use based on the type of implant that you have. If you're using a session in Sliver, this is essentially real-time communications. You can't exactly use an encoder that needs a couple seconds to encode data and then return it. This is going to cause some delays and essentially freeze your implant while that's happening, which is not great. So yeah, you notice this here, for example, if you try to encode a very large file, so 128 megs, it takes a few seconds. So this might cause issues in your session and cause it to freeze for a few seconds while that's happening. If you're using a beacon, it's less of an issue because if you have it sleeping for 30 seconds with some random variations there, this is fine. You won't exactly notice the time it takes to encode before sending it back. It's more in the case of sessions that can be a bit of an issue. And to give you a comparison, I also added a small base64 based encoder. Again, same idea, generates a bunch of random data, makes sure that everything is properly encoded and decoded, and then gives you an idea of the performance. And in this case, it's slightly faster using base64 as opposed to hex. So If we look at the code here, these are really just basic examples. It really just takes that buffer coming in, encodes it, returns it. Same thing with the base64, we're just using a different function here. So let's go ahead and generate an implant using these, or at least one of these custom encoders. So I'll just go back to my previous generate command and add a tag traffic encoders, and then I need to specify the name of the encoder I want to use. So in this case, I'll just use the hex.wasm one. You'll notice there's also an ID here. This is similar to the IDs we talked about previously with the what we call native encoders, so the ones that are written in Go. These will be used to identify and allow the server and implant to know which encoder is being used in communications. So if I go ahead and hit enter, this will generate, again, same idea as before. We copy over the implant code, we embed any parameters we need for that implant to communicate. And then we'll also embed in that implant the Wasm code for that particular encoder. So I'll go ahead and run this in another screen here. If you take a look at the debug output, you'll notice there's a couple extra lines here. Specifically, it's initializing the traffic encoder, unpacking the encoder that we've added here, the custom one, and you even see the ID here for referencing that particular encoder. If we take a look at the source code, so let's quickly switch here. Yeah, that's the one. And then in assets here, you'll see the Wasm code has been embedded inside the implant. If you take a look at the encoders.go, you still have the same default encoders here as before. The Wasm one is loaded in memory directly. The encoder for the Wasm one is essentially based on a SHA hash of the Wasm file, so you don't need to embed it here. It'll just be loaded at runtime. Right now, these need to be added when the implant is generated, but one of our goals would be to allow you to load those over the network and just switch up your communications on the fly. It's still something that's a work in progress, so for now, these just need to be embedded when you generate your implants. If we take a quick look below here at the code, we have this function here called random encoder. This is used every time your implant or your server want to send a message back and forth. They'll call random encoder. Random encoder will pick one of the encoders that are defined in the configuration above. So you have an array here called encoder map where all of these will be loaded in, and it'll just return one of those randomly. If you take a look at the function code itself, you'll notice there's actually an if-else. It'll start by using any custom encoder that you have. So if you've defined a Wasm encoder, it'll first try to use one of those Wasm encoders. If none of them are available, then it'll switch to using one of the default encoders written in Go. So it'll also have a small safeguard here. It doesn't try to use Wasm encoders for anything above 16 megabytes. This is really just a default threshold we've set up. Something you should customize based on the type of encoder and how you're trying to hide your traffic and the performance that you have there. This is really something that we're just testing out for now. So let's switch back to let's first run a command actually in our terminal. So if I use that implant that we generated, and again, just try pwd command, and then we jump back to Wireshark, we should see the same behavior as before, a GET request followed by a POST request. So the GET request, same as before, is the implant asking the server, is there any command available for me? And then the POST request is the implant uploading the results of that command to the server. One thing to keep in mind is if the result is big enough, you'll see multiple POST requests, not just a single one that you have here. So If we take a look at the traffic stream, again, same thing as before, but this time around, this is using hex, right? And if we grab the ID here and we decode it in our Python terminal, again, using the same modulus as before, we get 4472, and looking at our code here, this matches up the ID here for our Wasm-based encoder. Now, let's generate another implant, but this time we'll add both encoders in there. So our base64 one and our hex one. Just go ahead and hit generate. And then just run this in a separate shell. Cool. So if we so this time I'm gonna run a command that generates a bit more output. I'll just go ahead and use shell, then run something like top, for example, and leave it running for a few minutes. So it'll continuously upload the results back to the Sliver server. So if we take a look at the traffic here, just filter this for HTTP only. You can see we have multiple post requests going back and forth. The IDs keep changing. That's the whole reason why we have a modulus, is to not have a unique ID visible in those requests. So if we take a look at this one, for example, looking at the stream again, this one is using base64. If we grab a different one, we should also see the hex appear, and it'll kind of randomly shuffle between the two available encoders configured in the server side. The other interesting thing is you'll notice I only used a single Wasm file, which is loaded both on the server and the client. It's the same code as used on both sides. Which makes it a bit easier to ensure there's some consistency in the communication. Basically, it means we don't need to write a custom encoder decoder on each side, and we can just use the same one on both ends and ensure the communication stability in that sense. So that's mostly it in terms of content from my end. I'll open up to the floor if anybody has a question or would like me to delve into anything a bit further. So yeah, I've answered it in the chat, but I'm using an ARM laptop. One thing to keep in mind with the whole Wasm thing is we're hoping to offload a lot of the features in Sliver to Wasm, and essentially this should allow some time to slim down the size of the implant and instead load commands, for example, over the network into Wasm, and then from there run them directly on the hosts. So that's one of the reasons why we're slowly moving towards that. Let's see, EDR detection rate for the implant that's using the encoder. To be honest, I haven't had a lot of issues with EDR detection rates when it comes to purely network traffic based detections. It's really more on the behavioral side of things that we usually get caught. So for example, an easy example, there's the execute assembly. If you just run it with default parameters, it'll open up Notepad and inject into it. That's going to get caught by default. There are quite a few commands in Sliver that also have been signatured in recent years. So EDR evasion is going to be more around having a custom stager that can load it in memory, and then kind of how you run your commands. We tend to use a SOX proxy a lot, for example, to avoid any host-based detections. But the network side of things, it's not a usual detection we run into it. We have another question here. I haven't had success using custom interpreter implants on Apple ARM64. Have you had trouble with it? I haven't run into clients using ARM laptops yet, and I haven't used an interpreter in a long time, so I couldn't answer that one. But if you drop a message in Discord. We can take a look at some point after this. All right, Sean, I think that's it for questions.
All right. Well, thank you to everyone who joined, and of course for Tim for coming back and continuing the education of our community here on Sliver. I appreciate that. Couple quick notes. As I mentioned, this recording will be available on demand, usually within the first day or so. We'll link it here. It'll also be on our YouTube channel under the workshops playlist. If you didn't get a chance to ask your question live, you can drop it in the Discord server at any time. You can do it here in the Stages channel, but we have a dedicated Sliver channel too. So you can just hop in there and we'll get to that very, very soon. And yeah, if you have like 1 minute, I'm going to drop a link to a survey in here that we would greatly appreciate. I'm putting it in Discord. We're also going to put it on our website. So if you're just watching there, you can respond as well. If it asks anything specifically about Discord, you can move along. That's fine. But yeah, this will help us kind of get an idea of what you're looking for in the future and how things are going here. So yeah, once again, thank you so much, Tim, for stopping by. Thanks to everyone who attended, both here in Discord or, well, I guess as you see this, here in Discord or here on the website. Yeah, so have an awesome day and thank you very much.